Okay, good afternoon. If you remember, we were considering this figure that shows from left to right two bands. The density of states, gamma, the combined density of states, gamma, the Fermi statistics, P of E, and to the right, the product of gamma times PE, this is on top. And you remember that the area subtended by the curve gamma times P that is indicated by the arrow, the area is the concentration of the electrons of the conduction band. In the lower part, still on the right, we have the product of gamma times 1 minus P, but the valence band P is equal to 1. So the quantity in brackets is 0, and the product is also 0. That means that the concentration of holes of the valence band is 0. This also means that the valence band is completely filled with electrons, and as you remember, a band that is completely filled does not give any contribution to the current density. So the only possible contribution comes from the conduction band. Okay. This situation is typical of conductors. So like metals, for instance, have a situation in which the Fermi level is inside one of the bands, and this band takes the name of conduction band. And this is the only band that may contribute to the conduction, to the current density of the material. The question is, how much does it contribute? How big do we expect the current density to be? In general, you remember, conductors are able to carry a large amount of current. And this is because a parameter that you know very well, it is the conductivity of a conductor is large. Very soon we shall demonstrate that the conductivity, apart from constants, is proportional to the concentration of the carriers. Carriers is a general name that applies to the particles that are able to move inside the crystal, and so they are able to carry the current density. Okay, in this case, carriers are just only the electrons. In semiconductors, we shall see the carriers are electrons and holes. In the conduction band of a conductor, there are many electrons. So we expect that the conductivity will be large because the concentration of the electrons is large. We may also qualitatively try to understand whether the conductivity depends on temperature. Of course, when we talk about conductivity, we must think of the conductivity calculated at equilibrium, so some quantity that is proportional to the concentration. So since we are at equilibrium, we can talk also about temperature proper, okay? So assume that we change the temperature of the crystal, and then we estimate again the concentration. Now you remember well that when we change the temperature, we force a deformation of the Fermi statistics. In particular, if we increase the temperature, we find that the states that are above, in this figure, above the Fermi level, will have a larger probability of being occupied by electrons because the Fermi statistics goes up. In this case, since we have reversed the two axes, it goes to the right. Instead, the states that are below the Fermi level, for those states, the Fermi statistics will decrease. So they will be less populated, okay? In other terms, when we want to increase the temperature of the crystal, we give energy to the crystal from the outside. Some of this energy is taken by the electrons of the conduction band, and they go up in energy, so they become more energetic. That means that they transfer from the lower states still belonging to the conduction band and go into higher states of the same band. That means that the total number of the electrons of the conduction band does not change when we change the temperature. It is as if we have a room with some students sitting in the room, and the students just move from the seats where they are initially to other empty seats, okay? So the students move inside the room, but the total number of students does not change in the same room. If the total number of electrons of the conduction band does not change, the concentration also does not change. So the concentration of the electrons in a conductor, the concentration of the electrons of the conduction band in a conductor, does not change when we change the temperature. Since the conductivity is proportional to the concentration, if the other factors do not change, we expect that the conductivity should not change because of the change in temperature. Okay, actually, in the expression of the conductivity, there is another factor that we shall discuss in much more detail later. And this factor is called mobility. And mobility, when we increase temperature, mobility slightly decreases. Not that much, but there is a decrease in mobility due to the increase in temperature. So in a conductor, conductivity is the product of mobility, which slightly decreases, and concentration of electrons of the conduction band that does not change. So globally, the product slightly decreases. And this is very well known. If you take a piece of metal and heat it up, the conductivity will slightly decrease. Okay? So this completes the description of what happens in a conductor. That is a material in which the Fermi level belongs to a band. Now we have to consider the other case. That is the case in which the Fermi level belongs to a forbidden gap. And this is shown in this figure. We have the case in which, as you see, the Fermi level belongs to the forbidden gap. Actually, it is in between. It is not necessarily exactly positioned at the midpoint of the gap, but in many cases it is near the midpoint, okay? When the Fermi level is in the forbidden gap, the important bands are the bands that are immediately above, and this band is called the conduction band, and the other band is the band that is immediately below the Fermi level, and this band is called the valence band. Okay, we are using the same names. You can notice another thing, okay, that the extension of the gap is large. How large? Large enough to allow the Fermi statistics to completely go from practically 1 to practically 0 inside the forbidden gap. Okay, if you look at the central part of the figure, you see that the Fermi statistics is almost exactly equal to 1 in the valence band, going bottom up, okay? It is still 1 inside the gap, then it has a slope, it goes to 0, and when we enter the conduction band, it is already 0. What does it mean? It means that we have 0 probability to have electrons, or practically 0 probability to have electrons in the conduction band. So the conduction band is practically empty, which means that gamma times P is 0. And the valence band is completely filled. So again, gamma times 1 minus P is practically 0. So we have one completely empty band, that is the conduction band, and of course the other bands that are above the conduction band are also empty. And the valence band is completely filled, and the other bands that are below the conduction band are also completely filled. So in this material, there is no band that is partially filled, okay? They are either completely filled or completely empty. Therefore, there is no band that is able to contribute to the current density, and this material cannot have current density, so it is an insulator. So this is the typical situation of an insulator, okay? There is, however, another possible case that is still of this type, but let me change. Some of you is asking whether I can record on Teams. I'm recording with another method, and I'm then uploading the recording later, okay? I cannot record the pictures because they are copyrighted. At a later stage, in this module, the rest of the material will be also uploaded, okay? But this part is copyrighted, I cannot do it. So I was saying that if we change the material and we take another material like the one that is shown in this picture here, it is again the same situation. That is, the Fermi energy is at the mid gap, okay? But the extension of the gap is small. So if you look at the central part of the figure, you can see that when you enter the edge of the conduction band, the Fermi statistics is still non-zero. So there is a non-zero probability of occupancy of the stage of the conduction band. But at the same time, if you look near the edge of the valence band, the Fermi statistics is still significantly different from 1 near the edge. That means that gamma times P in the conduction band is non-zero. So there is a concentration of electrons in the conduction band that is given by the area subtended by gamma times P. But at the same time, also in the valence band, the product gamma times 1 minus P is non-zero. Okay? That means that both the conduction band and the valence band are partially filled. So they both contribute to conduction. The two populations, the population of electrons in the conduction band and the population of holes in the valence band, are not very big. They are much smaller than the population of the electrons in the conduction band of a metal, for instance, okay? Anyhow, they can contribute to the current density. So globally, the current density of this material will be smaller than that of a metal, but it will be non-zero. So this type of material has a conductivity that is intermediate between that of a metal and that of an insulator, okay? And for this reason, this type of material is called semiconductor, okay? When I say intermediate, it doesn't mean like 2 is intermediate between 1 and 3, okay? It's by orders of magnitude. We shall see it better later. It is of interest to understand what happens in a semiconductor when we change the temperature. When we change the temperature, for instance, when we increase temperature, the Fermi statistics will deform so that the probability of occupancy of the conduction band will increase. So the population of electrons of the conduction band will increase. But at the same time, the probability of occupation of the valence band will decrease. That means that the concentration of holes of the valence band will also increase. So in a semiconductor, we have two populations that both increase when we increase temperature. And this type of increase is exponential because it is dominated by the Fermi statistics. And as you remember, in the Fermi statistics, temperature appears in the exponent, okay? So the increase in population of electrons and holes at the same time will be large. Physically, this is obvious. Again, when we increase the temperature of a semiconductor, we give energy to the material, and some of this energy will be taken by the electrons, some electrons that are initially in the valence band. And they will make a transition to the conduction band. So some stage of the valence band will be depopulated, and some stage of the conduction band will be populated, okay? So in this case, when we consider the conductivity of a semiconductor, we have two competing mechanisms. One mechanism, you remember, conductivity is the product of mobility and concentration. So mobility will decrease when we increase the temperature. But concentration will increase. And the increase in concentration is much stronger than the decrease in mobility. So in a semiconductor, conductivity increases with temperature. So it is just opposite with respect to the metal, where conductivity decreases with temperature. Okay? One of you may ask, can we take an insulator, okay, and heat it up in order to have eventually a population of electrons in the conduction band and a population of holes in the valence band, so that we transform the insulator in a semiconductor? Well, no. We should heat very much, and there will be a phase change of the material before we can detect a change in conductivity. Now the issue is we must calculate the concentration. Since we are interested in a semiconductor, we actually must do two calculations. One is the concentration of the electrons in the conduction band, that is the area of this curve, and the area of this curve is the integral of gamma p over the conduction band. And then we have to calculate the area of this subtended by this curve, and this is the integral of gamma times 1 minus PE. So we must perform the calculation. Just 1 second. In order to perform the calculation, we need to calculate two integrals, okay? And these integrals are special integrals. So we must introduce some special function. Probably you already know about the Euler gamma function. The Euler gamma function is defined, as you can see in the first line. So gamma of some parameter lambda, by definition, is the integral between 0 and infinity of x to the power lambda minus 1 times the exponential of minus x integrated over x. Lambda may be even complex, okay? The constraint is that the real part of lambda must be positive so that the integral will converge. In our case, lambda is, of course, a real parameter. Gamma has a very special property. If you consider the case lambda equal to 1, you find immediately that gamma of 1 is equal to 1. Then gamma of lambda plus 1 can be calculated by parts, and you obtain that gamma of lambda plus 1 is equal to lambda times gamma of lambda. And this applies for any lambda. So in particular, it applies for gamma equal to an integer. So if you consider an integer, you have that gamma of n plus 1 is equal to n times gamma of n. But you can iterate. Gamma of n is equal to n minus 1 times gamma of n minus 1, and so on. So if you continue down to 1, you find the factorial. So gamma essentially is a generalization of the factorial, okay? Another important set of values of gamma are those for which the argument lambda is a half-integer number, okay? By some manipulation, you can transform the integral, the gamma of 1/2, okay, can be calculated as a Poisson integral. It's something that you should know from calculus, okay? So gamma of 1/2 is the square root of pi. And then all the remaining values of gamma for a half-integer arguments will follow as above. So gamma of 3/2 is 1/2 gamma 1/2, like square root of pi divided by 2 and so on, okay? This is a preliminary definition. Another definition that is fundamental for calculating the concentrations of electrons and holes are the Fermi integrals of order alpha. Okay, so the Fermi integral is indicated with the symbol phi. The suffix alpha is the order, and the parameter is indicated with psi, okay? So by definition, the Fermi integral of order alpha is the inverse of gamma of alpha plus 1 times the integral between 0 and infinity of x to the alpha divided by exponential of x minus psi plus 1 integrated over x. For the convergence of the integral, we must have that alpha must be larger than minus 1, okay? By an integration by parts, you see that the derivative of phi of alpha with respect to psi is equal to phi alpha minus 1. Why is this relation important? Well, you can observe from the definition that the Fermi integrals are all positive because the gamma function is by construction positive, and this integral also is by construction positive, okay? So phi of alpha minus 1 is positive for any alpha. That means the derivative with respect to psi is positive. So phi is an always increasing function of the argument psi, okay? When we calculate the concentrations, we don't need all the family of Fermi integrals. In general, we need only one type of Fermi integral, that is the Fermi integral of order 1/2. So when we want the Fermi integral of order 1/2, we let alpha equal to 1/2. So we here get gamma of 3/2, that is the square root of pi over 2. Then the exponent here is 1/2, okay? Calculating the Fermi integrals is typically very inconvenient, okay? So if possible, we shall try to avoid having to deal with the Fermi integrals, but there are good approximations for them. So some approximations are shown in the lower part of the page. And the one that we are going to use often is the first one. If the argument psi is sufficiently negative, meaning psi must be smaller than minus 1, then the Fermi integral can be approximated as the exponential of psi. And this is visible immediately, even if you take the general definition. If psi is smaller than minus 1, minus psi is larger than 1. So even for the smallest value of x, that is 0, the exponential dominates with respect to 1. So the integral here becomes equal to the definition of the gamma function, okay? So the gamma function cancels the gamma function that is in the denominator, and you are left with the exponential of psi. So it's an immediate calculation, okay? After defining the Fermi integrals, we can exploit them to calculate the concentration of the electrons in the conduction band and the concentration of the holes in the valence band. Remember, we are considering a pure semiconductor, okay? A pure semiconductor is also called intrinsic. So there are no impurities in the material. So by definition, this semiconductor is uniform in space. Okay, every physical point in space has the same physical properties of any other physical point in space. Okay, and we are in the equilibrium condition, so we can use the Fermi statistics. Now, consider the total number of electrons of the conduction band. Okay. Call it capital N sub E. So capital N sub E is the total number of electrons in the conduction band. Since the material is uniform, you can express the concentration simply by dividing the total number by the volume omega of the crystal. So this gives you the concentration N of the electrons in the conduction band. Since we are considering the intrinsic case, we attach an index I to the concentration of the electrons. So the index is just to remind that it means intrinsic, okay? Similarly, if we call capital NH the total number of holes in the valence band, then the concentration of the holes of the valence band will be the total number divided by the volume. So we have Pi is the concentration of the holes of the valence band. See, these are just two definitions, okay? The Fermi statistics is repeated here, okay? That is the probability of a state being occupied. So it is P equal to 1 over the exponential of E minus E sub Fi over Kt plus 1. You see the value of the Boltzmann constant here. And then we use simply the definition. The total number of electrons of the conduction band is given by the density of states G of the electrons in energy. So G is the density of states in energy, not the combined, okay? The combined is after the division by the volume. G is just the density of states. We multiply it by the Fermi statistics, and then you remember for the electrons of the conduction band, we must integrate over the conduction band. So we integrate from the lower edge of the conduction band that we call EC to the upper edge of the conduction band that we call ECU. Okay, so this gives you the total number of electrons in the conduction band. Similarly, we calculate the total number of holes of the conduction band, that is N, capital N sub H. It is equal to the density of state G. This density of states, of course, is the one that belongs to the conduction band, okay? Times 1 minus P, because we are calculating the concentration of holes, integrated in energy from the lower edge of the valence band that we call EVL to the upper edge that, as you remember, we call V, okay? Now we have a question. Do we expect that any relation exists between the number of electrons in the conduction band and the number of holes in the valence band? Well, we can easily demonstrate that these two numbers are equal to each other if we are considering the intrinsic semiconductor, okay? And in order to show this, we go back to the figure. And we assume that we are bringing the temperature to absolute zero, okay? When we bring the temperature to absolute zero, you remember the Fermi statistics becomes a box. So it becomes equal to 1 up to the Fermi level. Then it goes to 1/2, then to 0, and then it is equally, identically 0 above the Fermi level. So we know that all states of the conduction band at 0 Kelvin are completely empty, and all states of the valence band at 0 Kelvin are completely filled, because the Fermi statistics is a box. Now consider a slight increase in temperature, okay? A slight increase in temperature above 0 Kelvin, okay? When you increase the temperature enough, sooner or later there will be one electron of the valence band that will acquire enough energy to make a transition to the conduction band. If that happens, you have one electron, just one, in the conduction band and one hole in the valence band, because the transition of this electron has left behind a hole in the valence band. So you have one up and one down. When a second electron makes a transition, you have 2 and 2. And this continues forever. So the total number of electrons that are in the conduction band will always be equal to in equilibrium to the total number of holes in the valence band. And since the material is uniform, this equality also applies to the concentrations, because you just simply divide by the volume to go from the numbers to the concentrations, okay? So we have an important relation for the intrinsic semiconductor. It is explained in this line here, okay? At T equal to 0, the probability is 1 for E smaller than the Fermi level, 0 for E larger. So for any T, NE will be equal to NH, okay? So we must remember this relation. Given that, we consider any temperature, and we simply must calculate these integrals, okay? It is convenient to change the variable, okay? So when we want to calculate the integral over the conduction band, we observe that in the Fermi statistics, we have the difference E minus E sub f, okay? So the difference E minus E sub f can be expressed as E minus EC plus EC minus E sub f. We simply subtract and then add again EC. The difference E minus EC, you remember, is the kinetic energy of the electron. So it is something that is non-negative and takes the name E sub E. We already encountered this symbol, okay? The second difference is a constant. It is the edge of the conduction band less the Fermi level. So it is a difference that we call ZE. Be careful, because at this stage of the calculation, we don't know yet the actual value of the Fermi level. We just know that it is somewhere in the gap, okay? So ZE is something that is not, whose value is not known, okay? When we calculate the second integral, we must actually calculate 1 minus PE, okay? However, the Fermi statistics has an important property, okay? That take the expression of the Fermi statistic here. In this case, lambda has nothing to do with the parameter of the gamma function. Lambda is just the argument of the Fermi statistics written in short, okay, a short notation. So the Fermi statistic is P of lambda equal to 1 divided by the exponential of lambda plus 1. You can immediately find that 1 minus the Fermi statistics is equal to 1 divided E of minus lambda plus 1. So 1 minus the Fermi statistics is like the same Fermi statistics with the opposite sign in the exponent, okay? So when we want to calculate the second integral, actually in the exponent we have E of f minus E. So we have the opposite argument in the exponent. We can do the same trick, okay? We write E of Fi minus E equal to E of Fi minus EV plus EV minus E. So we just again subtract, in this case, EV and add EV. The difference EV minus E, we shall see, is the kinetic energy of the hole. Already, actually, we met this symbol when we expanded the E of k function to second order for the valence band. Okay, so E of h is non-negative. The other quantity, E sub f minus EV, is some value z of h that is still unknown because we don't know the position of the Fermi level for the moment. At this point, we simply replace this definition in the two integrals, so we have to replace here, and then we also must give a form to the density of state, and we use the parabolic band approximation because you remember the Fermi statistics is such that the electrons of the conduction band are pushed below near the bottom of the conduction band, and the holes are near the maximum of the valence band. So we use the parabolic band approximation. And you remember that in the parabolic band approximation, the density of states is proportional to the square root of the kinetic energy of the particle. So we do the calculation first for the electrons in the conduction band. That means that the integration limits are EC, the lower integration limit, and the upper integration limit is sum ECU, that is the upper edge of the conduction band. The density of states in energy, remember, is the volume of the crystal times some constant. MC is the total number of minima of the conduction band. ME is the average effective mass, and the kinetic energy is E minus EC. This goes under the square root. Then the concentration, you remember, is Ni, which is the total number of electrons divided by omega, but G is proportional to omega, so we just eliminate omega. We extract all the constants. We introduce the square root of E minus EC for the density of states. We divide by this denominator because this is the Fermi statistics. We integrate over energy. In principle, the integral should go from EC to ECU, but since this Fermi statistics has the exponent in the denominator, the integrand decays exponentially very quickly, okay? So we don't make a big mistake if we replace the upper limit ECU with infinity, okay? Because when we reach the energy ECU, the integrand is already negligible, okay? At this point, we remember that E minus EC is the kinetic energy, E sub E, so this square root becomes E sub E. The differential becomes dE sub E. The lower limit becomes 0. The upper limit stays plus infinity. And you remember we made some replacement in the exponent. So we have that the argument of the exponent, the exponential, is E sub E plus ZE. Okay? In the integral, of course, we integrate over the kinetic energy E sub E, so ZE is a constant parameter, okay? Then we change the variable by letting, you see in the exponent we have E sub E over KT, so this ratio is called X. Then the other quantity, ZE over KT, is called minus psi E, okay? But since we are defining a new variable that is X, okay, with KT in the denominator, here in the differential we must divide and then multiply by KT, so we have a KT in front of the integral. And then again, the square root must be divided and multiplied by square root of KT, so eventually we have KT to the 3/2. So we have Ni equal to constants times an integral that is almost equal to a Fermi integral of order 1/2. What is missing? Well, you remember we have the gamma function, so we must divide and multiply by the gamma function. When we multiply by the gamma function, we have square root of pi over 2, and then this is the final expression that is in the this line, okay? We can make an observation. The observation is that the left-hand side is a concentration. That is a number divided by a volume. The Fermi integral is a pure number, it's dimensionless quantity. So all the quantities together that appear as coefficient of the Fermi integral must have the units of a concentration. So we define capital NC, that is all this quantity here. Then we can simplify a little bit, because square root of 2 and 2 simplifies, square root of pi and pi squared simplify, etc. So NC is a concentration, is a constant concentration, whose expression is here. You can see in the last line of the page. So in compact form, Ni, the intrinsic concentration, is given by a constant Nc times the Fermi integral of order 1/2 of parameter psi e. Okay, the constant Nc takes the name of effective density of states of the conduction band. Remember, psi e is proportional to Ze, and Ze contains the Fermi level. So for the moment, we don't know the numerical value of the parameter, because we don't know the position of the Fermi level, but we shall find it very soon. So now we stop for 10 minutes, and we shall resume at 4:40. If there are questions, you may start the mic and ask the question. Okay, we start again. Do you hear me? Okay, so now we have now to repeat the analysis for the holes in the valence band, but the analysis is almost identical. We start from the density of states of the valence band, G of E, that is written in the first line. Here, M of V is the total number of maxima of the valence band. It is equal to 2 because there are 2 branches of the valence band. And MH is the effective average mass of the valence band. EV minus E is the kinetic energy of the hole. So the steps that we have to go through for calculating the concentration of holes, that is P sub I, are exactly the same as for the electrons, only the symbols change. So at some point we define the parameter of the Fermi integral as psi h, and this is minus ZH over KT. And if you remember, ZH is the difference in energy between the Fermi level and the upper edge EV of the valence band. At the very end, the calculation is similar to that of the electrons in the conduction band. So the intrinsic concentration of holes is equal to NV times the Fermi integral of order 1/2 parameter psi h, okay? And NV is called the effective density of states of the valence band, okay? And its expression is here, okay? Now we have 2 independent expressions. One is the expression of Pi just found, and the other one is the expression of Ni just found, okay? But both expressions embed the value or the position of the Fermi energy, and that position is unknown so far. How can we fix the problem? Well, we remember that we made a reasoning such that, or that showed us that NE, total population of the electrons in the conduction band, is equal to NH, total population of holes in the valence band, okay? So since the material is uniform, when we divide by the volume of the crystal, we obtain that the concentration of the electrons in the conduction band must be equal to the concentration of holes in the valence band, okay? So if we impose that Ni is equal to Pi, and we make the 2 expressions equal to each other, we obtain this relation. This relation is still insufficient to solve the problem, because in this relation we have two different unknowns. One is psi e, the argument of the Fermi integral for the electrons, and the other one is psi h, the argument of the Fermi integral for the holes. But these two arguments are not independent, because if we sum up psi e and psi h and put a minus on top, okay, you remember from the definition that minus psi e is equal to ze over kt, and minus psi h is equal to zh over kt. Ze is Ec minus Ef. Zh is equal to Ef minus Ev. So the Fermi level cancels in this expression here. And we are left with the difference Ec minus Ev. And this difference is equal to the gap of the semiconductor. And the gap of the semiconductor is known. We can calculate the gap of the semiconductor, or we may also measure the gap of the semiconductor, okay? So that the two quantities, psi e and psi h are not independent, okay? So we have essentially two relations, the first line and the second line, with two unknowns, psi e, psi h. So in principle, we can calculate psi e and psi h. And at this point, after calculating psi e and psi h, we know the position of the Fermi level, okay? Because psi e and psi h are proportional to the distances of the Fermi level from the conduction band and or from the valence band, okay? In practice, this calculation is complicated because as you can see from the second line, this calculation involves the Fermi integrals, okay? So it is rather complicated. However, for the special case of the intrinsic semiconductor, we can make an estimate, okay, of the position of the Fermi level. How can we make an estimate? This is quite simple because you remember, if you take silicon, Mc is equal to 6. Mv is equal to 2, okay? So we have a factor of 3 on the left. On the other hand, the effective mass, the average effective mass of the electrons is smaller than the effective average mass of the holes, okay? So the smallness of the effective mass of the electrons almost compensates for Mc being larger, okay? So we may say that the product Mc times M sub E 3/2 is almost equal, not exactly, but almost equal to Mv times Mh to 3/2, okay? So for the estimate, we simply take this coefficient exactly equal to each other, okay? We cancel Mc, Me to the 3/2 and Nv, Mh to the 3/2, okay? This is not formally correct because these two coefficients are almost equal, but not exactly equal, okay? But for the estimate, this is sufficient, okay? So if we cancel the coefficients, we find that the Fermi integral of order 1/2 of psi e is practically equal to the Fermi integral of order 1/2 of psi h, okay? But remember, we observed on commenting this definition here, this property, we found out that the Fermi integral is a monotonic function of the argument, okay? So if a monotonic function of the argument takes the same value for two different values of the argument, the only possibility is that the two arguments are equal, okay? There is no other way out if the function is monotonic. If the function is non-monotonic, think of a parabola, you may have the same value of the function for two different values of the argument, but in this case, the function is monotonic. So in practice, the estimate demonstrates that psi e is almost equal to psi h, okay? If we impose this equality here, we find that ze is almost equal to zh, but the sum of them is equal to the gap. So if of them is equal to half gap, okay? In conclusion, this estimate that applies only to the intrinsic semiconductor tells you that, at least for silicon or for the semiconductors of interest, the Fermi level is practically, not exactly, but practically at the mid-gap, okay? Is this estimate useful? Yes, it is, because it allows us to simplify the Fermi integrals, okay? Consider the case of room temperature, okay? At room temperature, that is TL around 300 Kelvin, remember KT is of the order of 26 milli electron volt, 26 milli. EG for silicon or germanium or gallium arsenide is about 1 electron volt. So we have 1 electron volt compared with 26 milli, okay? 1/2 EG is still much, much larger than KT. That means that psi E and psi H are much, much smaller than -1, okay? So the estimate provides us with the possibility of using the simplified form of the Fermi integral, okay? Because it shows us that at least at room temperature, psi E is much smaller than -1, and at the same time, psi H is also much smaller than -1, okay? So you remember, when that happens, we may approximate the Fermi integrals with exponentials. And of course, this is much, much more convenient because exponentials are easily manageable, okay? So now we take again the general expression of Ni and Pi. You remember it used to be Nc times the Fermi integral. Now we write it as Nc times the exponential of the same argument. And the argument psi E, as you remember, is minus 1 over kT times Ec minus the Fermi level. Similarly, Pi is Nv exponential of psi H. That is Nv times minus 1 over kT EF minus EV. Okay, so we have reached the conclusion that thanks to the properties of the Fermi integrals, at least for the intrinsic semiconductor, we can use the exponential approximation of the Fermi integral. At this point, since we remember that the concentration of the electrons Ni and that of the holes Pi are equal, it is not necessary anymore to use two separate symbols for them. It is customary to use the same symbol Ni for both the intrinsic concentration of the electrons and that of the holes. Okay, so instead of, for instance, if we take the product NiPi, this is important. It is called the equilibrium product of the concentration. Okay, since Pi is equal to Ni, we can write it down as Ni squared. Okay. Then, when we take the product here of the right-hand sides, you see immediately that the Fermi level cancels in the product, and we are left with Nc Nv times the exponential of minus the gap over kT. The gap is, you remember, Ec minus Ev. Okay. This product of the effective densities of states of the bands are taken from the definition. You see the product Nc and V, since Nc and Nv separately are proportional to kT to the 3/2, the product is proportional to kT to the cube, okay? You remember also the effective masses depend on temperature, because the effective masses are the inverse of the curvature of the band, and when you change the temperature, the band deforms, okay? But the dependence of the effective masses on temperature is very weak, so it is neglected, okay? So eventually, we have an easy expression for Ni or Ni squared, okay? This easy expression is this, okay? And if we take the square root, we can calculate Ni, okay? It is important in this respect to determine the dependence of the intrinsic concentration on temperature. You remember when you increase the temperature of the semiconductor, both the electron and hole concentrations increase. Okay, so it is important to understand how they depend on temperature. So the question is, where are the dependencies on temperature of this equation, of this expression? Well, of course, one is that we have kT in the denominator, okay? Another dependence is that the product Nc and V is proportional to kT to the third power, okay? And finally, we have another dependence, because the gap also depends on the temperature for the same reason as for the masses, okay? Because when you change the temperature, you deform the lattice, okay? So the dependence of the gap on temperature is not simple. It can be calculated, okay? Or it can be measured, and the results of the measurements can be arranged as a series of measurements that we can interpolate with an algebraic function or an analytic function, okay? So a very popular interpolation for the dependence of the gap of a semiconductor on temperature is shown in the last line, okay? This is just an interpolating function that works pretty well, okay? So we can express the dependence of the gap on temperature as a constant minus a parameter that we call alpha times the square of temperature divided by temperature again plus another parameter beta. And these three numbers, these three parameters, e.g. 0, alpha, and beta, depend on the semiconductor. Alpha and beta are positive. That means that when we increase temperature, the gap tends to decrease because we have the minus sign in this expression, okay? So when we set T equal to 0, that is at 0 Kelvin, we have the largest value of the gap, that is E sub G0. We can interpolate from the experimental data the value of the gap at 0 Kelvin. Parameter beta, of course, has the units of a temperature, and parameter alpha is such that when we multiply alpha by a temperature, we have an energy. So alpha has the same units as the Boltzmann constant, okay? So we have made quite a step because we started from a formal calculation of the intrinsic concentration using the Fermi integrals. We made an estimate. Thanks to the estimate on the position of the Fermi level, we were able to find the approximate position of the Fermi level in the gap. Given that we could use the approximation of the Fermi integrals and replace them with exponentials, and now we have a very simple expression of the intrinsic concentration. And probably we have a set of table or graphs. Yes. If you take the square root of Ni square, you obtain Ni. So you can see on top, Ni is the square root of Nc Nv times the exponential of minus gap divided by 2 kT, 2 because we have taken the square root, okay? The tables show the values of the parameters for the three important semiconductors. So on the first line you see germanium, the second line silicon, and the third line is gallium arsenide, okay? So you see that Eg0, that is the gap at 0 Kelvin, is about 0.7 electron volts for germanium, 117 for silicon, 152 for gallium arsenide. Then we have alpha and beta, the parameters that are used for the interpolation of the gap function. Then we have the gap at room temperature, Eg of Ta. You see it is smaller than the corresponding value of Eg0, okay? So germanium, you remember germanium is a narrow gap semiconductor. It is 0.66, sorry. Silicon is the reference material, 1.12 electron volts. Gallium arsenide is a wide gap semiconductor, 1.43, okay? Then we have the average masses. You remember, you already have seen tables involving masses, but those were the longitudinal and transverse masses, okay? These are the average masses, so they are obtained by, remember, the cubic root of the product of the transversal and longitudinal, so their numerical values are different, okay? So the average effective mass for the electrons is point, as usual, it is given in relation to the mass of the free electron M0, okay? So those are the values, okay? They are slightly smaller than the mass of the free electron, okay? Then we go to the second table, in which we see the effective density of states, okay? And the effective density of states are concentrations, as you remember. So here the units that are used are 1 over cubic centimeters, okay? Again, they are calculated at room temperature because you remember they depend on temperature, okay? So the effective density of states for the conduction band is of the order 10 to the 19th per cubic centimeter, and the coefficient is 1 for germanium, 2.8 for silicon, and 4.5 for gallium arsenide. The effective density of states for the valence band, again, is of the order of 10 to the 19th, and we have 0.43 for germanium, about 1 for silicon, and again about 1 for gallium arsenide. Okay, so they're very similar actually to each other. So if you look at the expression on top of this page, the expression of the intrinsic concentration Ni, you see that the square root of Nc and V is very similar for the three semiconductors. It is of the order of 10 to the 19th, okay? However, if you look at the last column of the second table, you see that the intrinsic concentration at room temperature is very different. Why? Well, for germanium, we have about 10 to the 12 electrons or holes per cubic centimeter, okay? For silicon, we have something slightly less than 10 to the 10th, so it is more than 100 times smaller, okay? And for gallium arsenide, we have 10 to the 6th with some units in front, okay? So you see that the intrinsic concentration from germanium to silicon to gallium arsenide changes by several orders of magnitude, okay? Despite the fact that the coefficients, the effective density of states are similar, okay? Why is it so? The reason is in the gap. The three materials have a different gap, okay? The difference in gap does not look enormous if you look at the fourth column here in the first table, okay? However, the gap is divided by kT. kT at room temperature, you remember, is about 26 milli. So if you divide by a very small number, you have a very large ratio here, okay? So even small differences in the gap are amplified by the exponential, okay? So you see that a narrow gap semiconductor like germanium has a very large intrinsic concentration. And an intermediate gap material like silicon has an intermediate that's about more than 100 times smaller intrinsic concentration, and a wide gap semiconductor has an even smaller intrinsic concentration, okay? Is this important? Yes, it is very important, because we shall see that if you take the very simple example of the p-n junction, and every electron device has some p-n junction in it, the saturation current that is the current that flows through the PN junction when it is reverse biased, okay, is proportional to the square of the intrinsic concentration, okay? So if the other parameters are all equal, a PN junction made of germanium will have a much larger saturation current with respect to silicon, and silicon much larger than gallium arsenide, okay? But the saturation current is a loss, is a waste of energy, is something that we don't like, okay? So germanium is not so good for, with respect to silicon, for manufacturing devices because of this, because the loss is much higher, okay? Gallium arsenide would be better, but gallium arsenide, as we noticed earlier, is a compound semiconductor, okay? So the technology is much more complicated. At this point, since we know that we can safely use the exponential approximation for the concentration, you remember when we made the estimate, okay, we exploited this equality and we eliminated the coefficients, imposing that the two coefficients are equal, which are not, okay? Now we can repeat the calculation more exactly by using the exponentials instead of the Fermi integrals, but we keep the coefficients, okay? So we make a more precise calculation of the position of the Fermi level. We repeat the analysis. We impose Ni equal to Pi. We keep the coefficients because they are actually different from each other, but we use the exponentials, okay? This calculation is elementary, and what we find is that the distance of the Fermi level from the edge of the conduction band is equal to half gap, okay? This was the estimate, okay? In the previous estimate, we found out that the distance is equal to half gap, okay? It is not exactly equal to half gap. This more precise calculation showed this, okay? It is half gap plus a correction. But this correction is small because, first of all, KT is much smaller than half the gap, or KT is much smaller than the gap at room temperature, okay? But also, we have the log of this ratio, okay? So these two numbers, MC times ME to the 3/2, that is in the numerator of the log, and the other one that is in the denominator of the log. These two numbers are different, but not very different. So the ratio is near 1, not exactly 1, but near 1. And the log of a number that is near 1 is very small, is near 0, okay? So actually the correction is small. One can consider that, okay? So in practice, we can say that in these semiconductors, okay, the Fermi level is practically at the mid gap, okay? Here we have a graph that shows the dependence of the intrinsic concentration on temperature. I go back for a second to the expression, okay? We want to make a graph of the function that is in the first line, okay? This function depends on temperature, as you remember, because the square root in front of it depends on temperature. because Eg depends on temperature, and then we have the explicit dependence on temperature in the denominator. The last dependence, the one that is in the denominator, is by far the strongest, okay? So as a first approximation, we consider only the dependence on temperature of the denominator here, okay? When we want to express a function of this form that is proportional to the exponential of minus a constant divided by temperature, we use a special type of graph, okay? So instead of expressing n, we express the log of n, okay? So the log of n will be a constant minus Eg over 2kt, okay? And instead of expressing the right-hand side as a function of kt, we express it as a function of the inverse of t, okay? So obviously, the log of ni as a function of the inverse of t is linear, is a linear function with a negative slope because of the minus, okay? So when we use a graph of this type, meaning that we consider the log of the function in terms of the inverse variable, we say that we are using the so-called Arrhenius plot. Arrhenius is indicated here. This one, okay? This is the Arrhenius plot. It means we are using the log of the function in terms of the inverse variable. And as expected, we obtain a straight line with a negative slope. It is even more convenient, instead of using the inverse temperature, to use 1000 divided by the temperature, because room temperature is about 3 something, okay? So the horizontal axis has 1000 over T. So when you see 1 here in the horizontal axis, that means that the temperature is 1000 Kelvin. 2 means 500. 4 means 250. Okay, so temperature increases from right to left here, okay? And the vertical axis is a logarithmic scale, okay? So the 3 dots here, here, and here are, respectively, the intrinsic concentration at room temperature. So the vertical dashed line indicates room temperature, okay? So you remember we have about 10 to the 12th for the intrinsic concentration of germanium at room temperature, about 10 to the 10th for silicon, 10 to the 6th for gallium arsenide. But if you go to 1000 Kelvin, you go up to 10 to the 18th, okay? So the intrinsic concentration becomes much, much larger at large temperatures. And as we anticipated, it increases with increasing temperature, okay? So far, we have discussed the behavior of the crystal considering energy, okay? We have integrated over energy and so on. And we have made a calculation of the intrinsic concentration. This figure refers to space, is another representation useful for discussion, but we don't have time. No, we do have still 10 minutes, sorry. So we can discuss this figure easily, okay? You remember silicon has a structure of the crystal that is cubic, and the elementary unit of this cubic arrangement is a tetrahedron. So we have one silicon atom surrounded by other 4 silicon atoms that are symmetrically placed in the 3-dimensional space, okay? This is the correct description of the crystal, but this description is not very convenient for graphics, okay? So it is customary to use a non-realistic description of the silicon crystal. That is the one that is shown in this page, such that we place all the silicon atoms on the same plane. Of course, this is not true, okay? But all the silicon atoms are pushed on the same plane. And of course, each silicon atom in the silicon crystal is surrounded by other 4 silicon atoms. So this is a rather clean picture. It is not realistic, but it is clean. And you see that if you look at the left part of the figure, you see that each silicon atom has pairs of sticks that connect it to the surrounding atoms, okay? So each stick is an electron. So each silicon atom has 4 electrons in the outer shell, and these 4 electrons form the bonds with the other silicon atoms, but also the neighboring silicon atoms also have 4 electrons, okay? So if you take any silicon atom and go to the right, there are 2 sticks. One is the electron that is, in quote, belongs to the left atom, and the other is the electron that belongs to the right atom. Of course, we cannot distinguish which is which. So we have 2 electrons forming a bond between the 2 silicon atoms, okay? The left part of the figure represents the situation at 0 Kelvin. At 0 Kelvin, there is not enough energy in the crystal to make any electron free to move. So all electrons are forced to stay attached to the corresponding atoms. There is no possibility for them to acquire energy and ionize the atom, okay, and become free electrons, okay? So the left figure shows that all electrons are confined in the vicinity of an atom. They cannot move around in the crystal, so there is no possibility to have a current circulating in the material. If we go on the right part of the figure, and we assume that we are in an equilibrium condition, but at some temperature higher than 0, okay? In order to go to a temperature higher than 0, that means that we have provided energy to the crystal. So if you remember the picture of the bands, okay, in the case of the left part of the figure, the Fermi statistics is a box. So no electrons in the conduction band, no holes in the valence band, no current. If you consider the right part of the figure, we are at some temperature different from 0. That means that some of the electrons have acquired enough energy to detach themselves from the atoms. Okay, so these electrons in the diagram of energy have become electrons belonging to the conduction band. And in space, they have become free electrons. So the black dots are electrons that have freed themselves from the atom, so they can move around in the crystal, okay? Since the crystal is in equilibrium, the motion of these electrons will be random, okay? So they will compensate each other and they will not provide any current, okay? But if we apply an electric field, the field will orient the free electrons and we shall obtain a current, okay? But there is another effect. You see, in the vicinity of the places where the electrons have become free, instead of having two sticks, we have one stick, okay? Because there is an electron missing, okay? So when there is an electron missing in the vicinity of a silicon atom, the form of the potential energy changes in the vicinity of the atom, and it becomes possible for another electron that is attached to the atom to move to the empty position. Okay, so a movement of an electron in one direction can be described as a movement of a hole in the opposite direction. Instead of having a negative particle that moves northeast, you have a positive particle that moves southwest. Okay, so if you look at the center of the right part of the figure, you see the arrow. Okay, the arrow describes a hole that moves from the upper right position to the lower left position. Okay. These are actually movements of electrons, okay, but we prefer to describe them as movements of holes in the opposite direction. These electrons move from one atom to the other by tunnel effect. It is a quantum effect that we don't have time to describe, okay? The point is that we have another family of particles that are able to move inside the crystal, and they are the holes, okay? Again, in the condition of equilibrium, the movement of the holes will be random, so they will compensate each other and there will be no net current flowing through the material. But if there is an electric field applied to the material, this electric field will also orient the holes besides orienting the electrons, the free electrons, okay? So we shall have two families of particles able to move inside the material and give contributions to the current, okay? So this is a qualitative description of what happens in a semiconductor. When you free an electron, you also free a hole, okay? And both will be able to move. Besides, this cannot happen in a conductor. In a conductor, you have free electrons, but there is no possibility for these tunnel effects to happen and provide a contribution also through the holes. So in a conductor, you have only electrons moving around. In a semiconductor, you have both electrons and holes, okay? Okay, so we stop. If there are questions, you can put the mic on. And otherwise, we shall continue in about 10 minutes. Okay, so we continue now. You remember that we were discussing the same situation as we did using the energy diagram. We were discussing the same thing using a space, an approximate space description of the silicon crystal, in which we are using a two-dimensional representation, which is non-realistic but very useful, actually. We were talking about currents, okay? So how do we formally define the current, or better, the current density associated to the electrons of a band, or associated to the holes of a band? We simply start again from the occupation probability of the states, as we already did when we defined the concentrations. So we now define the current densities, and we start with the definition of the average velocity of the electrons, okay? As we did before, we consider any band, the band of index J. So in this case, J is the index of any of the bands of the semiconductor, okay? And you remember that at some point, we have defined the concentration of the electrons of the band using the expression that you can see in the denominator here. So we take the combined density of states in the R and K space Q. So this Q, you remember, is 1 divided by 4 times pi to the third power, okay? This is a general non-equilibrium condition. So phi is the general probability of occupancy or occupation of a state K at position R at time t in the crystal, okay? When we integrate, consider the expression in the denominator. When we integrate this quantity over a band, we obtain the concentration Nj of the band. J is the index of the band, okay? So this is something that you already know, okay? Now look at the numerator now of this, and assume that U of K is the velocity of the electron whose momentum or average momentum is proportional to K, okay? In a parabolic band approximation, velocity and momentum are just proportional, like in the classical mechanics, okay? In classical mechanics, for a conservative force, P is equal to the mass times the velocity. In a crystal, P, that is something proportional to K, is equal to the mass tensor times velocity, okay? But if we consider an even more general situation in which we are not using the parabolic band approximation, the velocity of the single electron is some function of momentum that we do not specify for the moment, okay? So U of K is some function of momentum that we are able to calculate, okay? Then we take this velocity, that is the velocity of the individual electron, we multiply by the combined density of state, then we multiply by the probability phi, okay? We integrate over the band and we divide by the other integral, okay? You can see from the ratio of the two integrals that this is equivalent to taking the average of u. So this is by definition the average velocity of the electrons of band number j, okay? Because it is the integral of u with the probability normalized to the integral of the probability, okay? If you now observe that the k vector is saturated by the integration, the average velocity turns out to depend on position r and time, okay? Depends on position and time. And we call it v. So v is a vector because u originally is a vector. The index n indicates that we are calculating the average velocity of electrons, and j that these electrons belong to the band number j, okay? And we also remember that the integral in the denominator is the concentration of the electrons of this band. So if we now multiply both sides by nj, we obtain that nj times vnj is equal to this integral of u q phi, okay? So now we can specify some properties, okay? One property is obvious. If we are considering a band with no electrons, okay, that is a band in which every state is empty, then for that band, the probability phi is identically equal to 0. That means that this integral at the right-hand side is 0, so the product n times average velocity is also 0, okay? In the notes, there is a misprint, okay? So if any of you has a copy of the notes, this n is missing, okay? This is a typo. You should put nj here, okay? Now, let's take the opposite case. Let's consider a situation in which all the states of the band are filled with electrons, okay? That means that phi is equal to 1, okay? So phi in the integral is equal to 1. Q is a constant, so we can bring the constant outside the integral. So when phi is equal to 1, the average velocity is calculated by simply integrating u over the Brillouin zone. Okay, this is interesting because it can be demonstrated that in all situations, the function u of k is odd. Odd means that u of minus k is equal to minus u of k. Okay, this is true in every situation. Doesn't really matter what is the form of u, okay? U is odd with respect to k. Since you are performing the integration of over the Brillouin zone, and the Brillouin zone is centered in the origin and is symmetric with respect to the origin, when you integrate a function that is odd over a symmetric interval, you obtain 0. Because for every positive contribution to the integral, there is a negative contribution equal in modulus. Okay? So if phi is equal to 1, so if every state is filled, then the average velocity is equal to 0. Okay? So we have found two situations in which the product concentration times velocity is 0. The first situation is when the band is empty. The second situation is when the band is completely filled, okay? But you can immediately observe that the product of the concentration times the average velocity is the flux, okay? So a band that is empty cannot have any flux. And this is obvious because there are no electrons. A band that is completely filled with electrons also cannot have any flux because for each contribution that is positive, there is an equal and opposite contribution to the flux that is negative, so they cancel each other. Okay, so this explains why a band that is completely filled cannot contribute to the current, because the current is proportional to the flux of the electrons. Also, another observation is that if we are in the equilibrium, phi is some function that is, as you remember, the Fermi statistics in the equilibrium condition. The Fermi statistics may be different from 0 and different from 1, is some function, but the Fermi statistics depends on energy. Energy is even, but U is odd. So the product U times phi is odd, and again the integral over the Brillouin zone gives you a 0. So at equilibrium, even a band that is partially filled cannot provide any contribution to the current as expected, because at equilibrium we do not have any current. Okay? Now, can we translate this in the language of the standard electric theory? Well, yes. If you take the band of index J and consider that this band has a concentration of electrons equal to Nj, each electron has a charge that is minus Q. Q is the absolute value of the electron charge, that is 1.6 times 10 to the minus 19th Coulomb. And from the standard electric theory, you remember that the current density associated to a the current density associated to a charge density is equal to the product of the charge density times the average velocity of this charge density. Okay, but the charge density is minus Qn, so eventually the expression of the current density of band number J is minus Q and J, V and J. So we have demonstrated that there are three situations where the current density of the band is 0. One, when there is no charge, so no electrons. Second, if the band is completely filled with electrons. And number 3, if the band, although it is partially filled, is in the equilibrium condition. Okay? Now we have to check whether we can repeat the analysis for the holes. Okay? And this is easy, actually, because Consider again the current density of band number J, okay? The thing that we just have defined a minute ago. So it is J and J, N stands for electrons, the small j is the counter of the band, is equal to minus Q and J, V and J. And this is defined by this integral, you remember, is the integral that we have been using before after multiplication by minus Q, okay? Then you remember phi is a probability. So phi is a number that is limited between 0 and 1, okay? And we use again the old trick of expressing the probability phi as 1 minus 1 minus phi, okay? So we simply express phi in this form and we replace phi in the integral, okay? So what do we obtain? Well, we obtain an expression of the current density of the band number J that is made of the sum of two blocks. The second block comes from this minus, okay? It is minus Q integral of U, but you remember U is odd, and the integral goes over the Brillouin zone that is symmetric with respect to the origin. So the second integral is 0, okay? And we are left with the first integral, okay? And the first integral is, you can see, is an average velocity taken on the empty states, because instead of using phi, that is the probability of the state of being filled, we are using 1 minus phi, that is the probability of the state of being empty. So we are considering an average velocity of the empty state, but we multiply it by Q, not minus Q, because in the manipulation we have a minus and this minus cancels the other minus. So we are expressing the same current as before. It is just the same current density, sorry, of band number J, as if it were due by the empty states carrying a positive charge. Okay, so this starts introducing the idea that if we consider the holes instead of the electrons, we may still calculate the current, but we must ascribe a positive charge to the holes. Okay, we may elaborate a little bit more on this because you remember we already calculated the concentration of the holes using the probability phi as this integral, the combined density of states times 1 minus phi. So let's take the expression of the current density here, and then let's divide and multiply this current density by the concentration of the holes. What you obtain is this last formula. When you multiply by the concentration of the holes, you have Pj, concentration of the holes of the band number J given by the integral above. When you divide by the same quantity Pj, you use the expression of the integral. So you see the ratio of the two integrals is the average velocity of the empty states, because it is the average of U calculated with 1 minus phi and normalized with the integral of 1 minus phi. Okay, so we call this ratio average velocity of the empty states or average velocity of holes, Vpj. And we are left with the coefficient Qpj. Okay, so this is exactly as before, is the current density of band of number or of index j. We can express it alternatively, either using the electron concentration and average velocity with the minus, or using the average velocity of the holes, the concentration of the holes, and the plus sign with the charge, okay? If we prefer using the holes, then it is useless to call it capital J NJ, we call it capital J PJ. It's just the same thing with a different symbol, okay? And in the last line, we have that the charge density due to the holes, of course, is QPJ, and the current density is QPJ VPJ. So using electrons or holes in this representation is completely equivalent. Okay, you see that it's a pure mathematical manipulation. For each band of the semiconductor, in principle, we could decide to use either the electrons for describing concentration and current density, or the holes for describing concentration and current density of the bands, okay? Because these expressions are found one after the other by mathematical manipulation. The question is, why do we then prefer using the electrons in the conduction band, and we prefer using the holes in the valence band? And the reason is that when we use the electrons in the conduction band, the electrons are near the bottom. So we can use the approximation of the parabolic bands. And the usefulness of this comes out in the dynamical description, okay, because we have the effective mass. Similarly, when we consider the valence band, you know that the holes that are the empty states are near the top of the band. And again, in this case, we can use the parabolic band approximation for the holes. So we have a simplified description of the dynamics. This is the reason why eventually we use the electrons in the conduction band and the holes in the valence band. This part is referred to the dynamics, but we have already gone through it using the notes, so we don't need it. This is just a memo. We already described the expansion of the E of k relation around, for instance, a minimum. We are using the symbol K0, but it doesn't really matter. It is like K, okay? This is useful because it shows that when we have the second derivatives of E of k, you remember the second derivative divided by h bar squared gives you the inverse element of the mass tensor, okay? So the inverse elements are those that can be grouped in a matrix, as you see on the right here, okay? So 1 over M1A, M2A, M3A are considered as the diagonal terms of a matrix or of a tensor, and this is called the inverse mass tensor, okay? And you already remember that in each valley of silicon or germanium, for instance, two of these three elements are the transverse masses and the other one is the longitudinal mass. If you have a diagonal matrix, the inverse matrix is the matrix in which the elements of the diagonal are the inverse of the original elements, okay? So when you invert m to the -1, you obtain M, this matrix here, in which the diagonal elements are just the inverse of the other ones, okay? If you use the symbol of this diagonal matrix, the kinetic energy can be written in compact form here, which looks like the expression of classical mechanics, because h bar delta k is momentum. You have another momentum, you have like momentum square over 2 times the mass, okay? So this is just to show that it's similar to the classical situation, okay? So far, with the intrinsic semiconductor, okay? You certainly know that in the majority of cases, the semiconductor is not intrinsic. The semiconductor actually, in standard devices, has in its volume a distribution of what we call impurity atoms, okay? The impurity atoms that are used in silicon, remember that silicon belongs to the 4th column of the periodic table of elements. That means that each silicon atom has 4 electrons in the outer shell, okay? Using suitable technological processes, we are able to introduce into the silicon crystal atoms belonging to other chemical species. And these atoms are called impurities, okay? And they are inserted purposely into silicon because we want to change essentially the conductivity of silicon, okay? The types of material that are used for silicon, they go under the general name of dopants, okay? And the distribution of dopants is called the doping of the semiconductor. The types of materials that are used for silicon are materials that belong either to the 5th column of the periodic table of elements or to the 3rd column of the periodic table of elements, okay? So we shall see both examples. And in this case, we start with the figure that represents the situation in space. And we take the example of an element, of an impurity, belonging to the 5th column of the periodic table of elements, typically phosphorus. So we imagine that we have introduced atoms of phosphorus into the silicon crystal. This introduction is made with special technological processes such that, as you can see from the figures, each atom of phosphorus takes a position in the crystal lattice of silicon, takes a position that would be the position of a silicon atom. When this happens, we say that the position of phosphorus is substitutional. So actually, this atom of phosphorus replaces one atom of silicon exactly in the same position that would belong to the original silicon atom. Okay? Another important information is that the concentration of the dopants is much, much smaller than the concentration of silicon. So we are not forming a chemical compound of phosphorus and silicon, okay? We just have still silicon with some atom from time to time, so to speak, replaced with phosphorus atoms. So the phosphorus atoms are far away from each other in the silicon lattice, okay? Each phosphorus atom is surrounded by many silicon atoms, okay? Now, an atom of phosphorus has 5 electrons in the external shell, okay? Because phosphorus, you remember, belongs to the 5th column of the periodic table of elements. What does it mean? It means that when the phosphorus atoms is introduced into the silicon lattice, 4 out of the 5 external electrons of phosphorus form the bonds with the silicon atoms, okay? Of course, the size of the phosphorus atoms is somewhat different, so there will be a slight deformation of the crystal, and this is not shown in the figure. It is not considered here, okay? So 4 electrons of phosphorus will form the bonds. So you see the pair of sticks that connect the phosphorus atoms with the surrounding silicon atoms. And then there will be the extra electron, the 5th, let's call it 5th electron of phosphorus that will not participate in any bond, okay? So this electron will orbit around the phosphorus atom, okay? It is indicated on the left part of the figure as a little black planet orbiting in the vicinity of the phosphorus atoms. Actually, we should describe it with quantum mechanics, so it will be a wave function of the electron that is around the phosphorus atom. So it's, in a classical description, it is like an orbit, okay? Obviously, the phosphorus atoms that we are introducing into silicon is neutral, okay, is a neutral atom. So in the phosphorus, there are as many electrons as protons, okay? So the charge of the orbiting electron is compensated by one of the protons of phosphorus, and this proton is, of course, positive, and it is symbolically indicated with that white dot in the phosphorus atoms, okay? Atom. So when we are at 0 Kelvin, nothing happens, okay? This is the situation that is shown in the left part of the figure. If we now go to a temperature that is non-zero, as we observed before, some of the electrons of silicon will become free electrons, and these will also make some holes of the silicon atoms free to move in the crystal. So we have a formation of electron hole pairs due to the silicon atoms. But in addition to that, the so-called fifth electron that was originally orbiting around the phosphorus atoms will easily find the energy to become free, okay, because it is loosely attached to phosphorus, okay, the bond is not so strong. So it will be easy for the electron that is originally attached to phosphorus to become a free electron. So the phosphorus atom will ionize. It will become positively charged because it has lost one electron, okay? So the phosphorus atoms will make one electron available for conduction of current in the silicon lattice, okay? But there will be no holes released by the phosphorus atoms because the form of the electric potential near the phosphorus atom is such that it is impossible for the tunnel effect to occur, okay? So the white dot of the phosphorus atoms will stay fixed at the position of the phosphorus atoms. In conclusion, the phosphorus atoms will make one electron available to silicon and no hole available to silicon. So it will make the population of the conduction band of silicon richer, okay, and it will give no contribution to the valence band, okay. Now the point is, how important is the contribution of phosphorus when compared to the contribution of silicon? And we can easily find situations in which the population of the electrons released by the phosphorus atoms will be dominant with respect to the population of the electrons made available by the silicon atoms. It's an easy example. Assume that the concentration of the phosphorus atoms is 10 to the 15th per cubic centimeter, okay? And we can easily find that at room temperature, each phosphorus atom releases its fifth electron, okay? So we shall find 10 to the 15th electrons per cubic centimeter released by phosphorus, whereas the typical figure of intrinsic silicon is 10 to the 10th, you remember. So a relatively small concentration of dopants of the phosphorus type will provide a concentration of electrons that is 5 orders of magnitude larger than that of the intrinsic silicon, okay? Another thing is that at room temperature, 100% of the phosphorus atoms will release one electron, okay, and nothing more. It's impossible for the phosphorus atom to release 2 electrons, for instance, okay? So the number of electrons released by phosphorus atoms not only is dominant with respect to that of the electrons released by the silicon atoms, but also is independent of temperature, because 100% in typical situations, 100% of the dopants release one electron, okay? So By using this concept of dopant, we have two advantages. One is that we control the conductance of the material, because we simply control the conductance by deciding how many atoms of dopant we introduce into the silicon material, to the silicon crystal. Second, at least for a large interval of temperatures, we make conductivity independent of temperature. This is an enormous advantage, okay? Pure silicon, you remember the Arrhenius plot, has a dependence of the concentration on temperature that is exponential. That means that also conductivity depends exponentially on temperature. So even a small change in temperature will change the performance of a device made of pure silicon enormously. If we introduce a relatively low dose of dopants, we stabilize conductivity, we control its value, and we make it independent of temperature. So using the dopant is of enormous advantage for the applications. This is the description in space. As you expect, we then must also use the description in energy and eventually recalculate the concentrations of electrons and holes when you have a dopant in the material. We do not have time to do it today. We shall do it on Tuesday, but we have just a few minutes. What I want to do is, what happens if instead of using a material like phosphorus that belongs to the fifth column of the periodic table of elements, we use a material that belongs to the third column. A typical example is that of boron. Boron belongs to the third column, okay? So the situation is formally dual with respect to that of phosphorus, okay? It looks more complicated in a diagram based on a space description like this, okay? We should better use quantum mechanics, but in these few minutes, we shall use just the dual situation. We start again from the condition at 0 Kelvin, and we have a material like boron that belongs to the third column. So boron has only 3 electrons in the outer shell, okay, not 4. So there is 1 electron missing for boron, okay? So qualitatively, in order to complete the 4th bond, boron creates an electron-hole pair. So boron, it's like creating 1 electron that is used to complete the bonds with silicon, but boron is neutral, so it must also create a hole, okay? So you see, this is purely qualitative description, of course. You have a hole that is the white dot that orbits around the boron atom and is compensated by the electron that is the black dot inside the boron atom. This happens at absolute 0 temperature, okay? When you have a temperature that is non-zero, well, it happens what happened with phosphorus, just in the dual situation. The orbiting hole is released, And this eventually will be found to be a hole that belongs to the valence band. So in this case, we enrich the valence band, and the boron atom will stay negatively ionized. So there will be an extra negative charge in the boron. And in addition to that, we shall have the usual creation of electron-hole pairs given by the silicon atom. So in the case of a dopant of this type, we enrich the valence band with holes. And again, we can control the number of holes of the valence band very easily. And also we make the conductance of the material essentially independent of temperature. So you see, in a semiconductor, we have two dual possibilities. When we use boron, like in this figure, we enrich the valence band of holes. Holes are, as you remember, positive carriers, okay, positive. So we also call boron a dopant of the p type because it provides extra positive charges to the valence band. Instead, phosphorus, you remember, provides negative charges, that is electrons, to the conduction band, and for this reason we call phosphorus, or the other materials of the fifth column, we call them n-type dopants. Okay, so we have the possibility of doping silicon with either P or N, and as you know, in the technological application, both types are used in different regions of the material. So for the moment, we can stop. If you have questions, please use the mic. Otherwise, we'll meet each other next Tuesday. Okay. Thank you.